Hi everyone, here is our last review session for Math 111. Today what I'm going to do is work out solutions to the final exam, the practice version of it that I sent you a couple days ago. This should be pretty similar to what you'll actually see on the final exam. As a reminder, final exam, there's two different times you can take it, at least two different times you can take it with me. Monday from 1 to 3 p.m. in the art building. It's art building 101, I'll be there. And then again on Thursday from 8 to 10 a.m., kind of a horrible time. I'll be in that same room, Art Building 101. So if either of those two work for you, great. And if not, you can always take it with another proctor or something like that. Just, let me know what you need to do. So anyway, final exam. What you will see will be something that's laid out a lot like this. There's going to be 7 sections, I guess, I shouldn't call them problems. And it'll be worth, I guess it's 140 points, although the points don't really matter because, it's all based on the percentages that are laid out in your syllabus. And then there'll be an extra credit little problem at the end. And so the layout for it, what's going to happen is the first problem is going to be a bunch of true-false statements like we have here. So I'll go through and work out those. And then just as an FYI, the second problem will be a problem from your first midterm. The third problem will be a problem from your second midterm. So these problems straight off your midterms, copy, paste it, change a number or two, throw them back on there. Just an excuse for me to get you to review those old midterms. And then the remaining 4 problems will just one from each of our quizzes, basically one from each of the different topics that we covered in the last third of this class since our second midterm. So to give you an idea of what some of those topics are, here's the practice final. All right, so indicate whether each of the following are true or false. So the first one deals with function transformations here. It says to obtain the graph of this mess from this thing, what you have to do is stretch the graph vertically by a factor of 2 and shift the graph up by 3. It turns out that that's true. The way you can figure that out is really what's causing the transformation to what changes this into this is this 2 right here and this plus 3 right here. And both of them are affecting the f of x, the output, not the x. It's not 2 times this x in here, it's 2 times the output, the square root of x. So both of them are affecting the f of x, so they're both vertical transformations. And with vertical transformations, you always do the stretching first and then the shifting. So the stretching, the multiplication, this 2 here, is going to stretch it vertically by a factor of 2. And the shifting, this plus 3, is going to shift it up by 3. So anyways, that's true, is what we're trying to get at. Next one, very similar, except it's false. Gives you a function, gives you a transform function. So here we have this 2 and this 3. Very similar to what we have up here. The difference is now I'm affecting the x values. It's not 2 times the square root of x, it's 2 times x. I'm affecting the x values. X, you think horizontally. These are both horizontal transformations. Oh, that's what it says, horizontal. Right, but when you're doing horizontal transformations, everything's a little bit backwards. So you think you'd shift it right by 3. You don't. You actually, this means you shift it left by 3. You think you'd stretch it by a factor of 2? You don't. You actually stretch it by a factor of 1/2. Compress it by a factor of 2. Then lastly, there are actually 3 things wrong with this. The order, I believe, is backwards. When you're doing horizontal transformations, you do things in the opposite order. So up here I multiplied, then I added. Down here you add, and then you multiply. So this is false. What we do down here is we would shift left by 3, then compress by 2. And compress by 2, aka stretch by 1/2. So 3 things wrong here. Compress instead of stretch, left instead of right, and the order's wrong. You only need 1 wrong to be false. That's definitely false. The graph of this mess has a horizontal asymptote at y equals 0. Horizontal asymptotes is talking about end behavior. So for end behavior, there's 3 different cases you have to consider. If the degree of the numerator is the same as the degree of the denominator, then you get a horizontal asymptote at, so what I'm trying to get at here is this thing is going to act like x squared over 2x squared. When the x values get really, really large, this is going to overpower the 3x and the 2. You won't even notice these. Similarly down here, this term will be so large that this minus 2 won't even notice it. This is going to act like this when x gets really, really big. When we go towards infinity or towards negative infinity. This is just equal to 1/2. So what that's saying is when my x-coordinate gets really, really large, my y-coordinate will get really, really close to 1/2. When my x-coordinate becomes some really, really large negative number, my y-coordinate will get really close to 1/2. So what I have here is a horizontal asymptote at y equals 1/2. Therefore, this is false. It's not at y equals 0, it's at y equals 1/2. If you're wondering, anytime the degree of the denominator is bigger than the degree of the numerator, that's when you have a horizontal asymptote at 0. It's worth repeating. Anytime the degree of the denominator is bigger than the degree of the numerator, you get a horizontal asymptote at y equals 0. If they're the same like this, you get a horizontal asymptote at the quotient of the leading coefficients. What I'm saying is this 1 divided by this 2. Anyways, it's false. The graph of this thing has a vertical asymptote at x equals -1. Vertical asymptotes happen when the top is not 0 and the bottom is 0. So what I'm saying is if you factor this guy out, I get x plus 1 times x plus 2 divided by 2 times x plus 1 times x minus 1. If you factor this whole thing out, you get this. And if you look at this, the bottom equals 0 when x equals -1. We'll make all this stuff 0, but the top won't be 0. So when x equals -1, the top's not 0, the bottom is 0. That's the criteria for having a vertical asymptote. So this statement is true. If you're curious, when the top is 0 and the bottom's not 0, you get a root, aka a 0 or an x-intercept. When the top is 0 and the bottom is 0, you get a hole, or your book calls it a removable discontinuity. I'm trying to use fancy words, I guess. But this statement is true. -1 will make the bottom 0, not the top 0. Thus, we have a vertical asymptote at -1. Exact same function here. So the same factoring works. So it has a removable discontinuity at x equals -1. So you get this removable discontinuity. I don't want to write that word again. When the top equals 0 and the bottom equals 0. So if you look at our factored form here, the only value of x that will make the top 0 and the bottom 0 is -1. Shoot, I messed up. Okay, this is false. Going a little too fast through here. Note that -1 makes the top 0, but it also makes the bottom 0, right? This term right here, I didn't notice. Makes the top 0 and the bottom 0. We don't have a vertical asymptote there because vertical asymptotes only happen when the top is not 0 and the bottom is 0. So -1 makes the top and the bottom 0, therefore it's not a vertical asymptote. In fact, what it is a hole. It's a hole when x equals -1 because that makes the top equal 0 and the bottom equal 0. So at -1 we have a hole, not a vertical asymptote. Sorry about that. This one's true, this one's false. If the point 2,3 is on the graph of f of x, then the point -2,4 is on the graph of this mess. Kind of a tricky question. So we have two transformations going on in here. This negative is going to flip horizontally, and this +1 is going to shift up 1 vertically. So what I'm saying is I have this point 2, 3, 1, 2, 1, 2, 3. And it's on the graph of f of x. And then I transform that graph. So I take all the points and I flip them horizontally. So instead of being here, it's now over here. But then I'm not done. I have to shift it up by 1. So I get right here. So this point right here is on f of x. That tells us that this point right here is on f of -x plus 1. If the point 2, 3 is on the graph of this, then the point -2, 4, which is exactly this point, is on the graph of this. Yeah, looks good to me. Looks true. This point right here is -2, 4, and it is on this. The range of this mess. Okay, so what it wants you to recognize here is that the vertex of this parabola is at +1, -3. 1, 2, 3. If you think about this as a bunch of transformations of the graph f of x equals x squared, this 2 stretches it vertically by a factor of 2, but that won't move the vertex at all. This moves the vertex right 1, this moves the vertex down 3. In fact, the graph of this parabola looks something like I want to be careful when I draw because I don't want to miss points that I should. Looks something like this, roughly speaking. The range of this thing from 6 to infinity, no, the range is from -3 up to infinity. Range is from -3 to infinity. So this statement is false. That's the basic idea of what you'll see on the final in terms of true-false questions. About this difficulty level, you'll see some of these. You'll expect to see some of these rational function ones, some different types, but basically this difficulty level, this is a good place to test function transformation. I don't know, writing function transformation problems are a little hard to do, but putting them in true-false is a good place for them, so expect to see some of those also. You don't have to tell me why these things are true or false like I did. I just wrote these in here for your own sake. But if you just write true or false or T or F or whatever, that's plenty. You'll get full credit. All right, moving on. Number 2, I didn't put a number 2 on here. I'm just saying, look at your first midterm. I'm going to look at your first midterm, copy and paste one of the problems. It won't be the true-false problem, so one of the remaining ones. Change a couple numbers just so you can't memorize the answers, and put it in exactly the same. Not going to change any of the concepts, not going to change any of the layout. It'll be a problem. You'll recognize it from your first midterm. And you'll flip over to problem 3. And that'll again look familiar, except now it's straight off your second midterm. So that's what to expect on the final. This is the order they'll be in. They'll be the exact problems, just with different numbers. And then we'll move on. We got 4 more problems. And so we'll move on from quiz 10, 11, 12, and 13. That's 4. So on quiz 10, we talked about function composition. So here's an example of a function composition problem I could ask you. It says find f of g of f of x. When I'm given a problem like this, I like to rewrite it. I don't like this notation. I like to rewrite it like this. Just the order the letters are in and then the x with all these parentheses nested. And the reason why is writing it like this really helps you figure out what it's equal to. And the way you figure it out is you just replace from the inside out. What am I talking about? If you look all the way on the inside here, I have this f of x. I know what f of x is. It's 2x squared plus 3x. So instead of writing f of x right here, I can just write 2x squared plus 3x. This is equal to this. And so now what I have to do is replace g of this thing. So I say this is equal to f of something. And figuring out that something, the way I'll do that is I'll say, well, it's just g of 2x squared plus 3x. G of x is this thing. So like g of 5, for example, I just change all the x's into 5s. I don't want g of 5. I want g of 2x squared plus 3x. So what I'm going to do is copy this g of x thing, except everywhere I see the letter x, I'm going to replace it with 2x squared plus 3x. In other words, 1 divided by 2 minus 2x squared plus 3x. And now I'm almost done. I just have to figure out f of this thing. I know f of x is this guy. So again, f of 5, change this x into a 5 and this x into a 5. F of this mess, just everywhere you copy f of x, except everywhere you see an x, change it into this mess. So instead of 2 times x squared, it'll be 2 times this mess squared. X squared. And I'm not done. I have to add 3x. So instead of writing x, I write 2x squared plus 3x. Notice it says don't simplify. You don't have to work this all out. You don't have to do anything. Leave it just like this. It's fine. All I'm testing here is that you know how to compose functions together. Fine, but this time simplify g of x. Same idea for g of x. First rewrite it and start from the inside out. G of x is 1 over 2 minus x. Right, that's given to me in the problem. G of x is 1 over 2 minus x. So I want to figure out g of this thing. To figure out g of this thing, I copy g of x, except everywhere I see the letter x written, I replace it by this thing. instead of 1 over 2 minus x, I'm going to write 1 over 2 minus, and then put this in. Kind of weird. This is what you get. Oh, I'm not done. Simplify. It just said find. This is good. It says simplify, so I better simplify it. The way you can simplify it is, if we had a fraction over a fraction, we know how to deal with it. What's not simplified about this is kind of the fraction inside of a fraction. So what you got to do is figure out a way to make the denominator here a single fraction. The way you can do that is, the numerator, that's just 1 over 1. That's easy. That's a fraction. But in the denominator, I really have the difference between two things. Instead of 2, if you think about it as 2 over 1, then at least it's a fraction minus a fraction. I can deal with that. I just have to get a common denominator. So 2 minus x would be the least common denominator. So that'll be change colors a little bit here. If I multiply this little fraction here by 2 minus x over 2 minus x, note I'm not changing any values because this thing that I wrote in red is just equal to 1. What I would get is, leave the top alone for now. 2 minus x times 2, that's 4 minus 2x. And that's over 2 minus x. And then I want to subtract 1 over 2 minus x. But since I have the same denominator, I can just write it one time. The whole thing over 2 minus x. Now, I have a fraction divided by a fraction. The way you divide fractions, kind of like multiplying fractions, except you multiply by the reciprocal of the denominator. What I'm saying is take this thing and flip it upside down. Instead of this over 2 minus x, 2 minus x over this. If you want, instead of 4 minus 2x minus 1, you could say 3 minus 2x. I know that you have to simplify that at this step, but 4 minus 1 is 3. And then when I flip this upside down, I get this. This times 1, that's just 2 minus x over 3 minus 2x. This right here is the simplified form. Find and simplify g of x. Here you go. There it is. Decent chance that I will ask you to find and simplify a composition of two functions where both the functions are these rational expressions, these things as fractions. Good chance you are going to see this where you end up with fractions inside fractions. You'll have to simplify it in following these steps. So go through this example a couple times. If it doesn't make sense, talk to me. Let me help you. Look for old problems that are like these and work these out. That's going to show up, and the reason that shows up is because I want to ask you about the domain of this thing. Because it's kind of tricky. It's the one thing that most people get wrong when they talk about function composition. When you're looking at a function like g of x, and you want to know its domain, you have to check two things. You have to look at the domain of the inside function. In this case, the inside function is g of x. Inside these parentheses here, I have a g of x. They're both g of x's, so it's a little bit confusing. But I'm talking about this one right here. This where f of g of x would be g of x, the inside function. Check the domain of the inside function. In this case, g of x. And then you also have to check the domain of the composite function. So we have to check g of x, which is this 1 over 2 minus x thing, but then also the composite function, which is this 2 minus x over 3 minus 2x. That's why I was so insistent that you simplify up here, because I wanted to look at the domain down here, and you have to have the simplified form to see that it's the domain. What do you mean when you have to check two things? Well, what I'm saying is figure out what x's are not in the domain of this thing, and figure out what x's are not in the domain of this thing, and that'll be your domain. So from this one, x cannot be equal to 2. Set 2 minus x equal to 0 and solve, you'll get x equal to. If x is 2, we're dividing by 0 here. Dividing by 0 is bad. Down here, what do you end up with? 3/2 that x cannot be. If you set this equal to 0 and solve, 3 minus 2x equals 0. Same as 3 equals 2x, which is the same as 3/2 is equal to x. X cannot be equal to 3/2. Why can't x be equal to 3/2? Because if it is, this thing on the bottom is 0. This thing is on the bottom is 0, I'm dividing by 0, which is undefined. So what I'm saying is the domain of this composite function includes all numbers on our number line, except for 2. This guy right here. And 3 halves. Gee, that's a horrible draw. Let me try that again. So here's 0. There's 1. There's 2. There's 3. I don't want this number, and I don't want 3 halves. 3 halves is the same as 1 1/2. I don't want. It's 2 that I don't want, not 3. This number I want to kick out for here. And then 3 halves I want to kick out. That's this guy. So what I'm saying is I want all these numbers, and all these numbers. If you can't write your answer in interval notation, it says to, so you should. But at least draw me a picture or tell me in words what you're going for, so I can give you some partial credit for this thing. But really what it wants is all of these numbers, meaning everything from negative infinity all the way up to 3 halves. Oh, and then everything in between these two. So everything from 3 halves up to 2. And then everything bigger than 2, so everything from 2 up to infinity. So this is the perfect answer if you can get all the way to here. But if you can't, at least tell me, show me some work, show me something so I can give you some points. Key thing to know is when you're looking at the domain of a composite function, you have to look at 2 things, the domain of the inside function and the domain of the composite. Everyone forgets to look at the domain of the inside one. Make sure you don't just kick out 3 halves, you kick out 2 and 3 halves. All right, moving on. Number 5, material from quiz 11. So in quiz 11, we looked at what are called quadratic minimums and maximums. So the basic idea here is you're given a quadratic function, a second-degree polynomial, and asked to find things like the vertex, the y-intercept, the x-intercepts, sketching graphs, all that good stuff. Vertex, there's at least 2 different ways to do this. Option 1. Take the square. Most people think this way is harder. Option 2. The x coordinate of the vertex is always negative b over 2a. What I'm saying is that if a is the coefficient on your x squared term, and b is the coefficient on your x term, c is your constant term. Negative b divided by 2a, negative 3 divided by 2 times negative 2 is 3/4. Negative over negative is positive. 2 times 2 is 4. This is the x-coordinate of my vertex. So what you can do, it wants to know where the vertex is. Well, this is the x-coordinate. Once you know the x-coordinate, you can find the y-coordinate by plugging it into the original function. So whatever the hell this is equal to will be the y-coordinate of our vertex. See, this is 9/16 times negative 2 gives me negative 9/8. This is 9/4, which is 18/8 to get a common denominator for later. This 1 is just, 8/8. So negative 9 minus 8 more is negative 17. Plus 18 gives me 1/8. So what I'm saying here is my vertex is at the point 3/4, 1/8. Most people think this is the easiest way to do it. The other option is you can complete the square. What I'm saying is if y equals negative 2x squared plus 3x minus 1, I can complete the square to get it into my standard form. To complete the square, you want 1 as your leading coefficient. So let's add 1 to both sides. And then divide by negative 2. And what that leaves me with is just x squared minus 3/2 x. And now I can complete the square by adding b over 2 squared to both sides of the equation. So in this case, my b is negative 3/2. So half of that is negative 3/4. So that squared is 9/16. So if I add 9/16 to both sides of the equation, what I'm left with is a perfect square on the right-hand side. Oops, I forgot to write the 9/16 over here. Specifically, it's I have 9/16 plus y plus 1 over 2 is equal to x minus 3/4 squared. If you FOIL this all out, you get this. An easier way to know is this perfect square will always be x plus b, negative 3/2 over 2. So negative 3/2 divided by 2 is negative 3/4. So x plus negative 3/4 is x minus 3/4. So you get here, if you go and you solve for y, what you'll have is what's called the vertex form of this parabola. So what I'm saying is y plus 1 over 2 is equal to x minus 3/4 squared minus 9/16. And if you multiply by 2, you get 2 times x minus 3/4 squared minus 9/8. So finally, if you subtract 1 from both sides, I'm worried I'm not going to get the same answer. So I wonder what happened. Copy this down right, plus 1. No, that's right. Add 9/16 to both sides. Subtract 9/16. Maybe it's over here I messed up. So this was 3/4 squared is 9/16. 9/8 negative. Fourth. Oh, I can't tell. This looks right. Maybe I'll just continue with what I'm doing here. If I subtract 1 from both sides, I get y equals 2 times x minus 3/4 squared minus 17/8, which is not good. Okay, so there's a mistake somewhere in my work. I don't see it. Maybe you see it. Oh, you know what it is? Shoot. Okay, it was me being sloppy. What I did is I had a -2 right here, and I just didn't copy it over to this line. This should have been a -2 right here, which means this should have been a -2, which means this is a -2, which means this is a positive. Let me go back one step. Because this is a -2, this is a -2, this is a -2. So when I multiply both sides by -2, this becomes -2, and this becomes positive 9/8. There we go. So now when I subtract 1 from both sides, I'm left with just 1/8 over here. Positive. So anyways, the purpose, if you can get it all the way like this, now we can just look at this and tell where the vertex is. This is a lot like this problem, where you can just look at this and tell the vertex is at positive 1, -3, because it shifted to the right 1 and down by 3. The same idea here. This is going to shift it to the right by 3/4 and up by 1/8. So the vertex would be at 3/4, 1/8. It's a lot easier if I don't screw it up. Sorry about that. The good news is you don't need to know both of these methods. Do either method, whichever one you want. Most people think option 2 here is a little bit easier. I just thought I'd be some great teacher and show you 2 different ways to do things. And then I screwed it up and probably made things worse for everybody. Sorry about that. But it's right now, for what that's worth. Anyways, saving for myself. Moving on. Y-intercept. Good news about a y-intercept is it's easy to find. If you think about where a y-intercept occurs on a graph, it's just where you cross the y-axis. And the spot where you cross the y-axis is when the x-coordinate is equal to 0. So all I have to do is look at my function here and change all the x's to 0. To find the y-intercept, just make x is 0 and see what your function is equal to. -2 times 0 squared is 0, plus 3 times 0, just get -1. You can leave it just like this, or you can say it's at the point 0, -1. I don't care. Either of these are fine. I know what you mean. The y-intercept. That was a lot easier than finding the vertex. Finding the x-intercepts. Okay, there's at least 2 different ways to find the x-intercepts. One of them is reliant on you completing the square. Had you done this option 1, which I don't know if anyone's going to do it this way, but if you did it this way, I mean, basically the x-intercepts happen when the y-coordinate equals 0. So what you can do is just say 0 equals this mess and solve. That'll work. But if if you hadn't done this, you won't have this step. So you'd have to make 0 equal this thing. What I'm getting at is you have two options again. Maybe I can do it better this time. Because this really should be option 2 over on this side. If you found your vertex this way, you don't have this. So you can't use this later on. So to figure out the x-intercepts, you say 0 equals this negative 2x squared plus 3x minus 1. And you solve this equation. Lots of different ways you can solve this equation. One way is to complete the square. One way is to use the quadratic equation. One way is to factor. This one, factors, you find two numbers that multiply to positive 2 and add to positive 3. Those numbers are positive 2 and positive 1. And so what you can do is you can replace your middle term with, what did I say, positive 2, positive 1. And if you do that, now you have 4 terms that will factor by grouping. So you look for the greatest common factor between this first group. I don't know, 2x, negative 2x. You can do it either way. Maybe I'll do negative 2x. I'm going to do 2x because I think that's what most people would have thought to do. Either way is fine. If you factor out 2x, you're left with negative x plus 1. And then you want to be left with negative x plus 1 here. So what you have to do is factor out a negative 1. Now you have a negative x plus 1 in both terms. So you factor that out. Now this is gone and this is gone. And what you're left with is 2x minus 1. So what this is telling you is that either negative x plus 1 equals 0 or 2x minus 1 equals 0. Either x is equal to 1 or 2x is equal to 1, in which case x equals 1. So I have x-intercepts at this point and this point. Another option, calling this option 1, because it kind of corresponds with option 1 up here. Had you done all this work, what you have is that y is equal to negative 2 times x minus 3/4 squared plus 1/8. So how does that help you? Well, the x-intercepts happen when y equals 0. So I can make this y equal to 0. I could say negative 2 times x minus 3/4 squared plus 1/8 is equal to 0. And then solve this for x. I think this is easier to solve for x than this is to solve for x. So we've kind of already done the completing the square form. Just want to get the x all by itself. Got to get rid of the 1/8, the negative 2, the squared, the negative 3/4. So first subtract 1/8 from both sides of the equation. Try to write a little bit neater. Now divide both sides of the equation by negative 2. Negative 1/8 divided by negative 2. Negative over negative is a positive. It's positive 1/16. If you have trouble seeing why 1/8 divided by 2 is 1/16, instead of dividing by 2, you can think about it as multiplying by 1/2. 1/8 times 1/2 is 1/16. Now you take the square root of both sides of the equation. If you take the square root, you have to make sure you put in the plus or minus. The square root of 1/16 is 1/4. Get you here. So finally, what you get is that x is equal to 3/4 plus or minus 1/4. Well, 3/4 minus 1/4 is a half. 3/4 plus 1/4 is 4/4. In other words, 1. Get to the same answers no matter which method you use. I think this way is easier. The problem with this way is you have to do this option, and this option's hard. So what most people do is they do option 2 in these two problems. But you can do whatever the hell you want. I don't care, whatever you're good at. Sketch an approximate graph of this parabola. Make sure to label the vertex and the intercepts. All right. I figured out that this parabola has a vertex at 3/4, 1/8. Better make this pretty big. There's 1 way up there. So 3/4 is like right here, and 1/8 is right in here. So here's 3. Try again. 3/4, 1/8. And then it's also supposed to have x-intercepts at 1 and 1/2. So there's 1, and there's 1/2. Should I figure out? I guess I did say the intercept, so I guess we should figure out the y-intercept also. Oh, we did that. Good. The y-intercept is -1. So really we want to make sure to label all 4 of these points here, or at least put big dots and then put them at the right spot so I can tell you know what they are. And connect them, draw something that looks something like a parabola, goes through those points. Good enough. It's supposed to be symmetric. I'm not a good artist, so it doesn't really look symmetric, but we'll call that good enough. Vertex, x-intercepts, y-intercept. Good enough. Moving on. Material from quiz 12. So in quiz 12, we're dealing with polynomials, but unlike quiz 11, they're not just second-degree polynomials. They can be bigger polynomials. For example, a fourth-degree polynomial. And it'll ask us stuff like determine the end behavior, determine the y-intercept, find zeros, blah, blah, blah. Start from the start. Determine the end behavior. For end behavior, you only have to look at this term right here. Because my leading coefficient is a negative number, when x goes to infinity, y is going to go towards negative infinity. So because this is a negative, this is negative. If this has been positive, this will be positive. So look at the leading coefficient and whether it's negative or positive, and that tells you whether to put a negative or positive here. And then you have to look at the degree of the polynomial. You have to look at this number up here, the 4 up in the exponent. If this is an even number, then the thing that you write right here is the same as the thing that you wrote up here. So in this case, because it's even, these two are the same, negative infinity. Had this been odd, you'd write the opposite of what you wrote there. What I'm trying to say is there's really 4 cases when the leading coefficient is negative and the exponent is even. You get this as your end behavior. You get something that looks like this. I don't know what happens inside the circle. It does all sorts of weird stuff. When you go to the left, it goes down. When you go to the right, it goes down. That's what this is saying. When you go to the right, the graph goes down. When you go to the left, the graph goes down. So this picture, on the final, you can write this. That's best. But if you just have to draw a picture like this, show me you know what the answer is. I'll give you either all the credit or most. Y-intercept, that's an easy one. As we talked about above, we talked about that right here. Y-intercept happens when x equals 0. All you got to do is change all the x's into zeros. Same idea here. Change all these x's into zeros. F of 0 is 0 minus 0 plus 0 plus 0 minus 16. Leave it like that, or you can write it like this. I don't care. Either way is fine. It's just the value of your constant term, because all the terms with an x in them go to 0 when you change x into 0. Y-intercept, that. That's all. Given that x equals -2 is a 0, determine all remaining zeros and their multiplicities. If x minus 2 is a 0, okay, so you look at this big polynomial up here. We got -2x to the 4th, what else do I have? Minus 2x cubed, plus 12x squared, plus 8x, minus 16. This is my polynomial. It tells me that x equals -2 is a 0. If x equals -2 is a 0, that means when I set this thing equal to 0, and I solved, -2 was my answer. In order for -2 to be my answer, x plus 2 must have been one of the factors. Because when you get to this stage, you set each of these equal to 0. If I had x plus 2 equals 0, I'd subtract 2 from both sides and get x equals -2. So we're kind of working backwards. We're like, oh, if this is a root, then that must be a factor. That's all I did there. So because -2 is a 0, x plus 2 must be a factor. So x plus 2 times something equals this mess up here. The question is just, what is that something? Well, there's a couple of different ways you can do that. You can do polynomial long division or synthetic long division. I guess it doesn't matter. I'm going to do polynomial long division because I think there's more examples of synthetic long division in your book. In case you prefer polynomial long division, then you'll have examples of both. Both will work. Both you'll get full credit for. Both are really similar. They just don't seem like it. I'm doing polynomial long division. I want to get rid of one column each time. To get rid of -2x to the 4th, I put a -2x cubed up here. That's because -2x cubed times x is -2x to the 4th. And negative 2x cubed times 2 is negative 4x cubed. And now I subtract. Subtract, this goes away, good. Negative 2 minus negative 4 is the same as negative 2 plus 4. Negative 2 plus 4 is 2. So what I'm left with here is 2x cubed, and the rest of this stuff, 12x, 8x, minus 16. Now I want to get rid of this 2x cubed. To do that, I'll put a 2x squared up here, because 2x squared times x gives me 2x cubed. 2x squared times 2 gives me 4x squared, and I subtract. This column goes away. 12x squared minus 4x squared is 8x squared. I got 8x minus 16. To get rid of this 8x squared, I need an 8x up here, because 8x times x is 8x squared. 8x times 2 is 16x. And now if I subtract, 8 minus 16 is negative 8x. And so to get rid of this negative 8x, I need a negative 8 up here. Negative 8 times x is negative 8x. Negative 8 times 2 is negative 16. If you subtract, you get 0, which is good. I should get no remainder. That tells me that this thing is equal to negative 2x squared plus, cubed, plus 2x squared plus 8x minus 8. So given that x equals negative 2 is a 0, it must factor to this thing. To find all remaining zeros, I'll have to factor this guy. So to factor this guy, maybe I do that off to the side. Let's factor negative 2x cubed plus 2x squared plus 8x minus 8. A couple different ways you can do this. Something that strikes me is that there's a greatest common factor. So I would pull out a negative 2 from all 4 of these terms. Turns out you don't have to do that. I think it makes it a little bit easier if you do it. And then I look at this, 4 terms. The only method that I know for 4 terms is factoring by grouping. Let's see if this works by factoring by grouping. See, from this first group, the greatest common factor is x squared. So if I pull that out, I'm left with x minus 1. So I have to pull out something from this group to be left with x minus 1. If I pull out a negative 4, I'll be left with x minus 1. So inside these big parentheses, I have 2 terms, and they both have an x minus 1 in them. So I can factor out that x minus 1, and then I'll be left with this x squared minus 4. What I'm saying is this factors to negative 2 times x minus 1. X squared minus 4 is a difference of squares, so it's x minus 2 times x plus 2. The completely factored form of this polynomial is negative 2, this negative 2, this x plus 2, this x minus 1, this x minus 2, another x plus 2, completely factored. So if I want to figure out the zeros, I have to figure out what x's satisfy this equation. Negative 2 never equals 0. X plus 2 equals 0 tells me that x equals negative 2 is a solution. X minus 1 equals 0 tells me that x equals 1 is a solution. X minus 2 equals 0 tells me that x equals 2 is a solution. And then I got this factor, which I already figured out over here. Since this factor shows up twice, this one has multiplicity 2. Whereas this factor only showed up once, so it's got multiplicity 1. Similarly, this factor, this root, only shows up once, so it's got multiplicity 1. Finally, sketch a graph. Did all that work. Show what the graph looks like. Well, let's see. End behavior is supposed to go down on both sides. Y-intercept is supposed to be at negative 16. Sure, there's negative 16 right there. It's supposed to go through the points 1, 2, and negative 2. However, at negative 2, the multiplicity is 2. Whenever the multiplicity is even, that means it bounces. What do you mean it bounces? Instead of going through the graph like this, it's going to come up, hit, and turn around. How did I know it's going to come up instead of coming down? That comes from my end behavior. It goes down on both sides. It starts way the hell down here, comes up and bounces, and then gets through this point, because it has to go through that y-intercept, Then it's got to get up pretty quick because it's got to go through this x-intercept. Note it goes straight through. The reason it goes straight through is because this multiplicity is just 1, and 1 is an odd number. And then it goes up somewhere. I don't know how high it goes up, but at some point it turns around, starts going back down. Goes through this point. Note that it goes straight through instead of bouncing because the multiplicity at 2 is an odd number. And it ends up going down. Good. My behavior said it should go down on both sides. This picture does. We don't know how high up this loop goes right here. That's something you don't learn until you take a calculus class. So for our purposes, it's just an approximate graph. It looks something like this. If you make sure that its guide goes through these points, bounces off this one, happy. That's all I want. All right, moving on. I think this is the last one. I kind of hope this is the last one. This video is getting long. It is. Material from quiz 13. Find all zeros. Some of them are real, some of them are complex of this polynomial. So you look at this thing and you're like, I don't know how to factor this thing. I can't think of a great way for it to factor. So what you do is use the rational root test. The rational root test tells you that possible rational roots, so not necessarily all of the roots, but the possibilities are integer factors of the constant term, which is 5, divided by integer factors of the leading coefficient, which is 1. So the only integer factors of 5 are 1 and 5, and the only integer factor of 1 is 1. So the only possibilities are 5 over 1 and 1 over 1. Oh, and I guess they could be positive or negative. In other words, the only possibilities for rational roots are plus or minus 1 and plus or minus 5. These are not all roots. These are the possibilities. What we have to do is test these. Test the possibilities. So it's a multiple step process here. Your book calls it the 4-step process. Here's my 4 possibilities. Let's test them all. The way you can test it is if it's a root is the same as the x-intercept. An x-intercept happens when the height equals 0. So if I put this x value in, and the f of x is equal to 0, that means the height is 0. So in fact, it is a root. So let's try it. If we change all the x's into 1, we get 1 plus 1 plus 3 minus 5, which is 0. Got kind of lucky there. 1 worked. If it hadn't worked, I'd go on and say f of negative 1, f of 5, f of negative 5. But 1 worked. Expect on the final either 1 or negative 1 will work. I won't want you testing through a bunch of different roots. I'm going to make it work easily. Either 1 or negative 1. 1 works. So 1, 0 happens if the number x equals 1. If 1 is a root, x minus 1 must be a factor. So what I'm saying is this polynomial must factor into x minus 1 times something. My goal is figuring out what that something is. The way I can figure out that something is polynomial long division, or if you prefer, 3x minus 5 synthetic division. Either way will give you the exact same answer. To get rid of this x cubed, I need an x squared up here. That gives me x cubed minus x squared. And I subtract. This column goes away. X squared minus negative x squared is the same as x squared plus x squared. It's 2x squared. To get rid of this 2x squared, I need a 2x up here. Guess I should copy down all this stuff. 2x times x gives me 2x squared. 2x times negative 1 gives me negative 2x. And I subtract. This column goes away. 3x minus negative 2x is 5x. And to get rid of the 5x, I need a 5 up here. This nice little check. When I subtract, you get 0 as a remainder. That's a good thing. That tells me that this polynomial factors into x minus 1 times x squared plus 2x plus 5. I'm not done. I've just factored this out a little bit. But what I want to do is find all real zeros of this polynomial. What I want to do is set this equal to 0 and solve. It'd be nice if I could factor this more, make life easy. Find 2 numbers that multiply to 5 and add to 2. If you think about it for a while, I think you won't be able to find anything that works. It's unfortunate. So since we can't factor any further, we can just set each of these terms equal to 0. Because if this times this equals 0, then either this is 0 or this is 0. And so what we got to do is solve each of these different equations. So if you're solving these different equations, we could solve this one by adding 1 to both sides of the equation. This one's a little bit harder to solve. there's a few different ways you can solve this. It doesn't factor, but you can complete the square or use the quadratic equation. It's totally up to you which one of those two methods you use. I think the quadratic equation, most people already know how to do that, so I'll complete the square. You're going to complete the square. You want your x squared and your x terms alone on one side of the equation. And then what you have to do is figure out what numbers you add to both sides of the equation to make this a perfect square on the left. That number will always be this number divided by 2 squared. So 2 divided by 2 is just 1. 1 squared is 1. So it's +1 that I'm going to add to both sides of the equation. And so what that gives me on the left is a perfect square. In this case, it's x plus 1 squared. On this side, I got -4. So now I can solve this equation by taking the square root of both sides. The square root of -4 used to be something that we couldn't handle, but now that we have complex numbers, that's the square root of -1 times the square root of 4. Square root of -1 is I. The square root of 4 is 2. So what you get is this is plus or minus 2I. Give myself a little bit more room. So to solve for x, you subtract 1 from both sides of the equation. You get -1 plus or minus 2I. Find all zeros, real or complex, of the polynomial. Here's the real one. There's the two complex ones. Use your answer to part A to express this polynomial as a product of 3 linear terms, completely factored. I've almost done that already. Right up here, I got x minus 1 times this mess, but this isn't a linear term, it's a quadratic term. However, if 1 is a root, I knew x minus 1 is a factor. So if -1 plus 2i is a root, I know that x minus that thing, -1 plus 2i, must be a factor. Similarly, if -1 minus 2i is a root, I know that -1 minus 2i must be a factor. So what I'm saying is that this polynomial factors into these 3 linear terms. If you wanted to distribute these negatives through, you could, but you don't have to. You can leave it just like this if you want. F of x is equal to this. If you took the time to multiply this all out to FOIL everything, and then multiply by x minus 1, you get right back up here to where you started. I gotta pause this for just a second. All right, sorry about that little delay. I had to help somebody out that came to my office. The downside of recording using my office. So when we left off, we had taken this polynomial, this big mess here, and completely factored it. When they say completely, what they mean is factor it into linear terms. And the way you will do that is find all the roots, and then do x minus each of those things as the factors. And that's a bit of a lie. That's not everything you have to do. I mean, that's almost everything you have to do. The one other thing you have to do is make sure that there shouldn't be a coefficient out front, a number right here, like the number 2 or the number 3 or something. And the way you figure that out is the number that you have to write right here is your leading coefficient. What I'm talking about is you look up at this polynomial, the leading coefficient is a 1. There's a 1 on this x cubed. So it's just a 1 that goes right here. You don't even have to write it. But if this were 3x cubed plus blah, 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 and you factored it all out, found all the roots, you'd write all these, but then you'd have to put a 3 out in front. But in this case, it's a 1. This is the final answer. There's no more you have to do there. So the last problem is kind of working backwards. So what it's saying here is they're giving you all the zeros. They're saying we got a 0 at 3 plus 2i, 3 minus 2i, and -2. And they want to know what the polynomial must have been. And so you're kind of redoing steps A and B, but backwards. Kind of starting with step B, you're saying, all right, if 3 plus 2i was a root, then x minus 3 plus 2i must have been a factor. And if 3 minus 2i was a root, x minus 3 minus 2i must have been a factor. And if if -2 is a root, x plus 2 must have been a factor. And because it has multiplicity 2, that means that factor appeared twice. It's x plus 2 squared. So what we got to do is come up with a polynomial that would factor like this. Well, the way we can do that is by multiplying these all back together, FOIL things out. plus 2 times x plus 2, that's not too bad. It's x squared plus 4x plus 4. So it's a little bit harder. A couple different ways you can do this. I think the easiest way is to take this negative and distribute it through. So what that gives you is x minus 3 minus 2i for this one. And take this negative and distribute it through, and that gives you x minus 3 plus 2i. If you write one of them, I don't know if I've done this in a video yet. If you write one of them horizontally and one of them vertically, it kind of creates this little grid. It's called the box method. And it's basically just FOIL, except the acronym FOIL, first, outside, inside, last, only works when you're multiplying binomials. And since these have 3 terms, it's kind of a lot to keep track of everything hitting everything. So some people like to write them out in a box like this. All I'm saying is you do x times x is x squared, x times negative 3 is negative 3x, x times negative 2i is negative 2xi, x times negative 3 is negative 3x, negative 3 times negative 3 is positive 9, negative 3 times negative 2i is positive 6i, 2i times x is 2xi, 2i times negative 3 is negative 3, no it's not, it's negative 6i, and then 2i times negative 2i is negative 4i squared. But if you remember, I squared is negative 1, so it's negative 4 times negative 1 is positive 4. And what you'll notice in these problems is all the i's are going to cancel out. Negative 6i, positive 6i, these two guys cancel each other out. Negative 2xi, positive 2xi, those guys cancel each other out. So all I'm left with is x squared minus 3x minus 3 more x is minus 6x. 9 and 4 is 13. So what I'm saying is that when I multiply this times this, I get x squared minus 6x plus 13. And so what I have to do is multiply this times this. Do this box method again. A little bit tedious. X squared minus 6x plus 13. X squared plus 4x plus 4. X squared times x squared is x to the 4th. X squared times negative 6x is negative 6x cubed. 13 times x squared is 13x squared. X squared times 4x is 4x cubed. 4x times negative 6x is negative 24x squared. 4x times 13 is, what's that, 52? X. 4 times x squared is 4x squared. No, it's not. What happened here? Oh, no, I'm good. 4 times negative 6x is negative 24x. 4 times 13 is 52. And now if you add up all of these terms, what you get is your final answer, which we can write right here. How about this? I'll put an equals here, equals here, equals here. X to the 4th. See, I have 4x cubed minus 6x cubed, so I have negative 2x cubed. I got 4x squared, and 13 more x squared gives me 17x squared. But then I got to take away 24x squared. So what I get is negative 7x squared. 52x minus 24x is 28x. And then finally plus 52. Here is a 4th degree polynomial. And if you factored it, it would factor like this. And if you set those equal to 0 and solved, you'd get these as your answers. So it has these different zeros. So it must be our answer. If you're curious, it doesn't say find V, it says find A. It doesn't spell 4th right. I think that's like go forth and find. Go forth and take this test. It says A, not V, because you could have a 2 out in front of the whole thing. And I could multiply all these terms by 2, for example, and that won't change the zeros at all. So there's different answers. Probably the simplest is this one. But equally correct would be to multiply all of these terms by any number you want. But you still have to FOIL all this out, so the same work would still apply. This would work for the final answer. And I guess that's the end. So on the final, it'll be a lot like this, like in terms of difficulty. I made this and I made the final by going through your old quizzes, flipping through your homework, and taking problems that you guys did. I'm trying not to do anything unfair, no surprises. Everything should look like what you saw in the final. This practice final, what you saw in quizzes and homework. This practice final is a pretty good indication of what you'll see. Can't promise they'll be exactly this, but these concepts, these ideas, pretty fair. I'm also going to put some sort of extra credit at the end because I always do that. Because typically I make the test pretty hard. I don't know, this is pretty hard if you look through all this. So I like to give people an opportunity to get a couple extra credit points back if they want. Keep in mind on the final that I will be grading these, no graders or anything like that, which means lots of partial credit. Show me everything you can. It's okay if you can't get the right answer. Show me what you do know. You can't get part A and part B demands part A. Be like, I don't know what part A was, but if the answer were this, here's how I do part B. Show me anything you know so that I can give you points. I'm just looking for excuses to give you points on these problems. Lots and lots of partial credit. So do what you can. I'm sure you've realized that from your quizzes so far, from the midterms already. All right, this is getting kind of windy. I'll stop talking here. Good luck with all this studying. If anyone has any questions on anything, let me know. Otherwise, good luck with the test.